So, good morning, everyone. Welcome to lecture 14. So, in the last class, we actually finished chapter 2 of the book, and today we are going to start chapter 3. Okay, this is about motion, and also, so in the last several classes, we learned about different strains, we learned about stretch, we learned about change in angle, change in volume, change in area, then the polar decomposition. So now we will see how those quantities change with time. Okay, all those things that we learned, they were at a fixed time, and they were used mostly the gradient in space. The quantities, the strain, for example, is obviously gradient in space. But now we are going to learn how the strains are changing with time. Okay, so how the various strain measures that we learned, so how are they changing with time? So we'll try to derive their formula. Okay, this is very important for fluid mechanics people because they work with the strain rate, shear strain rate or extensional strain rate. But also for solid mechanics people also, if you are working with viscoelasticity or thermoelasticity or plasticity, you have to deal with strain rates. Okay, that's where the notion of solid and fluid start to mix up. So it is important for both of them, but certainly fluid mechanicians can't live without strain rate. Solid mechanicians, if they are just working with elasticity, they can be happy with strains. But fluid mechanicians, for them, it is very important. Okay. At the same time, fluid mechanicians usually don't bother much about strain, but solid mechanicians, they cannot live without strain. Okay, so there are things which are essential for solid mechanicians or for fluid mechanicians. But whatever we are learning, it's certainly good for everyone to know the strain rates. Okay, so let me give a recap of how we describe motion. So you can recall that the deformation map, which we denoted by y hat, remember? So this is of course a function of x, the referential location of a particle, and then also of time t, right? This is how we were describing motion, where this x is in the referential region, which is also denoted by r naught, okay, and y is in the current region, right? Current region occupied by the body. So we say it as RT. And your time t, it could be that you are interested in time between T naught and T1. Okay, it could be some T naught and T1. Okay, so if I again draw the picture, then there could be some, let us say, the origin O, with respect to which we are measuring all the positions. So the position of the particle in the reference configuration, that is small x, and its position in the deformed configuration or the current configuration, that's small y, right? And this is something which is a function of x and also time t, right? And this is the displacement being measured relative to the reference location of the particle. So that's u of x comma t. And then you can recall that um, the velocity, for example, we wrote v of x comma t as del of y hat by del t, isn't it? And this is, we denoted by v hat, for example, to show that this is actually the Lagrangian form because it's a function of referential location. And you also had the analogous v bar, so bar denoting the Eulerian form. So here things are functions of y and t. And how are these two related? So you simply say that this is equal to v hat, and in place of y you have that function y hat, right, which is depending on x comma t. And sorry, and there is of course t present explicitly also. So this, there is basically an inverse map also, no? So that means you have an Eulerian function x bar because it depends on y and comma t. So your v hat could be thought of through this Eulerian function x bar, right, which is actually depending on the location y comma t, and then you have this t also. Anyway, we had worked out all these things earlier, and similarly there is of course acceleration also, right? We worked out the Lagrangian form of acceleration as well as the Eulerian form of acceleration. Okay, we saw that in the Eulerian form, when you want to get acceleration through velocity, it had two terms, the local acceleration term as well as the convective acceleration term. Okay, whereas in the Lagrangian form of acceleration, it was looking quite simple. Okay, so having done that recap, let's what we want to say is that since now things are all functions of time, so we have, for example, deformation gradient f, that's a function of time also. So earlier we wrote f as just being function of x, but now it's a function of time also. Okay, similarly when we thought of polar decomposition, so earlier we were thinking of it just a position of x, but now it's a function of time also. Okay, so r being a function of both x and time times u being a function of both x and time. Okay, likewise for the other decomposition, v being a function of both x and time, and into r, which is a function of both x and time. So all the quantities are now functions of time. Even the lambda, the stretch, which we said is a function of x, and the direction of the line element n x, and now it's also a function of time. And the way to write this would be, so that's square root, right, and you had u square, isn't it, which is also c. So u square, which is a function of x and time, multiplied with nx, the direction of the line element in the reference configuration, right, and you dot it with further nx. Okay, and you also had lambda inverse, if you remember, right, which was the Eulerian form basically. So lambda inverse depending on the current position y and the current orientation of the line element ny, and then you have this time t here, and then you remember what you had here, v inverse square, isn't it? And in here you have of course x, but x you can write through the inverse map which is this x bar inverse through y comma t, right? And and then you have another time t, ny dot with ny. Okay, so this is the true Eulerian form. Okay, I think everyone is okay till now. Just a recap, right? Okay, so of course we derived several more things, and you can think that they're all now functions of time. And now the question is how these quantities are changing with time. That's the question that we want to ask now. Okay, so I think the motivation is clear to all of you. So let's begin with the example of rigid motion, where the body is not undergoing any change in shape or size. It's just undergoing rigid motion. So in rigid motion, the shape or size, they are not changing, right? It's the same. So how do we write down such a map? So I think you should all agree with what I'm writing here. So y as a function of time, and of course this y is now for a given particle x in the reference configuration, comma, time t, because we are not talking about motion, right? So can we say that this is equal to some rotation tensor q, which will be a function of time, multiplied by the position of the particle in the reference configuration, plus some rigid translation bt. So what is to be noted here is that q and b are independent of x. So they are independent of the particle. If q is identity, for example, special case, when q is identity, then y is simply x plus b. And that's an example where the body is going undergoing pure translation, right? So I can say here that for q equal to identity, motion corresponds to pure translation. Okay, and this by the way has another form also, and let me just mention that to all of you. So often we think that this rotation would be about some point x naught. Okay, you can call it x naught, y, or you can also call it z, for example, but it's some point z. So every particle is rotating about the point z. So the distance of the particle related to z, the distance will not change if it is rotation about z. Okay, and so you can say this then as such a motion, if the rotation is, let us say, by q and about z, then you can write such a motion as y equal to q into x minus z plus z. Do you agree with me? See, so here's the point O, and here is the point X. So this is x, this is z, okay, and this thing is x minus z. So what is rotating here is the vector x minus z. And therefore you have here q times x minus z. Okay. So this vector after rotation, that's becoming q times x minus z. Okay. And the picture is not nice here because this rotated vector must be of the same length, and here it is not of the same length. So, but maybe I can, you know, redraw it. So after rotation, it has to become q times x minus z. And we know that since it corresponds to rigid motion, so this particle, so the body would be something like this. Yeah. So now is this is more nicer. Okay. So this part is q times x minus z, and you have to add to it the position from O, this z, and that's giving you the final y. And this is what I wrote here. So y is equal to z plus q times x minus z. Okay. And if you make this z a function of time, then you are also trying to induce, you have translation part also in it. And of course, if you make this q as a function of time, then the body is kind of also rotating with time. There's some angular velocity also in that case. So there are two different forms to write the same thing. And if you try to correlate, then you can see that b of t is then equal to z of t minus q of t times z, right? You can relate these two forms, and you can work with either of the two forms as far as rigid motion is concerned. Okay, so having seen this rigid motion, let us try to find out what's the velocity. So velocity, as of now, we have seen that what we have to do is we have to get, so if I write velocity v, so of course it's a Lagrangian form, then it is simply del y by del t, right? Keeping x fixed. And so you come to the map, and then you have qt, so it becomes q dot of x plus b dot, isn't it? So I hope that all of you agree with me on this part. Now let us try to write this in Eulerian form. So as of now, this v is a function of x, no? But let us try to substitute x with y using this map. So from this map, you can see that x is equal to q inverse into y minus b, isn't it? X is equal to q inverse into y minus b. So let's just put that here, and then you will have q dot q inverse into y minus b plus B dot. And this we can sort of also write it as Q dot Q inverse times Y plus B dot minus Q dot Q inverse times B, right? It's very simple, mathematics being done here. And so this is Eulerian form because velocity is now in terms of the current position y. Okay, so you can see this is now in terms of current position y. And of course, this is not the general deformation, it's a rigid body motion. Please keep that in mind. So we are doing this just to motivate what will come later for the case of general deformable body. So if this is the velocity, let us also see what is this q dot q inverse going to be. What is the property of this q dot q inverse? So all of we know that q is a rotation tensor, right? So q is a rotation tensor, and therefore q inverse is same as its transpose, right? So we can write that this is same as q dot q transpose. And we also know for a rotation tensor q transpose, that's equal to identity, right? Because q transpose is its inverse, so q transpose is identity. Notice that q is function of time, but q into q transpose is a constant identity. Okay, so let's take the time derivative on both the sides. So let's do the dot ddt. So what do we get from here? What we get is q dot q transpose plus q into q transpose dot, that's equal to the zero tensor, right? Which is also meaning that q dot into q transpose is equal to minus of q dot q transpose. Sorry, I think I made some mistake here. Okay, yeah, so can I write this like this? So q dot q transpose whole transpose is same as q into q dot transpose. So this is what we have here, and it's coming right here. And minus sign because it goes on the other side of equality. But what does this mean? You see, if you call this as a tensor A, then A is equal to minus of A transpose. What sort of tensor is this? Anyone? A equal to minus of A transpose. Antisymmetric tensor, right? So that's the property of this q dot q transpose. So this is an antisymmetric tensor, and let us call this by W. So it's an antisymmetric tensor. And of course, it's a function of time. Okay, so with this in hand, we can say that v of y comma t, so which is the Eulerian form now, right? So that's equal to antisymmetric tensor W times y plus b dot minus antisymmetric tensor W times b. Okay, and from here, when you find out the Eulerian gradient of velocity, then what do you get? Remember what is Eulerian gradient. So Eulerian gradient is gradient of v, but with respect to the deformed coordinate y, or we actually wrote it as small g grad of v. So big G grad was the Lagrangian gradient, whereas small g grad is the Eulerian gradient. So can someone tell me what will be the Eulerian gradient here? Okay, let's try to work it out. So, for example, we can go back to indicial notation. So from here, suppose, so it's a vector form, of course, this thing within the circle, it's a vector equation, which means every term here is a vector. Let us try to write it in the coordinate system of e1, e2, e3. Okay, and then think of what will be then vi, the ith component of the velocity v. So can we say that vi will be equal to wij times yj, because you see it is w into y, no, matrix times a vector, so it becomes wij times yj plus b dot ith component minus wij bj. So I believe all of you will agree with me on this part. Now if that is the case, what is going to be del vi over del yk, for example? So this is, you come to the right hand side, and this w is not a function of y, so w acts as a constant, and then you have del yj over del yk, right? And the remaining thing is also not a function of y, so it becomes 0. And del yj over del yk is simply delta jk, and so this becomes wik, right? So del vi over del yk is wik. And what is this del vi over del yk? Isn't this the component of the gradient of velocity, what we are looking for, right? So if you put that back here, then what you're getting is w. So what you see is that the is Eulerian gradient of velocity is this w, big W. Okay. Actually, it turns out this big W has an interesting property. Can anyone tell me what is this W? Anybody? Can you tell me? It's obviously antisymmetric, but what physical property does it have? So can you guys recall that if W is antisymmetric tensor, then W times Y can be written as kind of cross product. So you can also write it as V of Y comma T, that's equal to this W vector cross product Y plus, of course, this thing B dot minus W vector cross product B. And what is this W vector? So many of you are saying vorticity. I think you guys are coming from fluid mechanics, so you're calling it vorticity. But more layman term, what is this W? Coming from mechanics, rigid body mechanics, what is this W? So it is angular velocity. So in rigid body mechanics, you have two velocities, right? One is translational velocity and the other one is angular velocity. So this W is angular velocity. Do you recall V equal to omega cross R? when you have circular motion. So here is that omega w. Okay, so that's the angular velocity. All right. So just to give you a recap, so your w is gradient with respect to y of velocity. That's a velocity gradient. Okay, and you will see that it's a very important term for deformable body. This velocity gradient will turn out to be an extremely important quantity. Okay, just like you have deformation gradient when you are working at a given time. Deformation gradient was mapping deformed line element and undeformed line element, right? It was present in the formula of stretch, present in the formula of angle change, present in the formula of volume change. You'll see that its velocity gradient will be present now in the formula for rate of change of those quantities. Okay, so it's extremely important quantity, velocity gradient. And if you try to also write in terms of curl, then this W, angular velocity W, is actually half of curl of velocity. Okay, which people also added half of. Curl is written as gradient, no? Gradient with respect to y, cross product del cross v. Okay, so remember it's the Eulerian curve. So you can show that quite easily that if this big W is gradient of v and small w is what is called axial vector, right? I think you have learned this in your math class also, axial vector of big W. So this is also equal to half of curl of v. Okay, and some of you were saying about vorticity, so vorticity is twice of this angular velocity. Okay, this is about rigid body motion. And what we came across is a very important term which is called velocity gradient, Eulerian velocity gradient, and this angular velocity term. Now let us see how does this velocity gradient look like when you have deformable motion going on. Okay, when it's not a rigid body motion but a general deformable motion. Okay, all right, so let's try to work that out. So this velocity gradient has got a symbol which is everywhere used in quantum mechanics literature, and it is called by L, second order tensor L. Okay, and it's an Eulerian quantity, so it's a function of y and time t, and it is, as you see here, it's the gradient with respect to y of velocity in the Eulerian form. Okay, so this is, we also wrote it as small g, small grad v, or you can also write it as del v over del y. Many people also write like this. Okay, and if you think of component form, then Lij is very simply del vi over del yj, isn't it? And just because L is the gradient, then what is Lii? You see from here, what is Lii? That's del vi over del yi, right? And there is summation over I. So what you get from here is that trace of L, TR for trace of L is equal to divergence of velocity, okay, which is also written as, this gradient term to y, but you have to dot it. It's the divergence, so divergence is gradient dot v. Okay. Now let us see, can we find out this formula in terms of deformation gradient? See, as of now, it's the Eulerian form of L. Can we get a Lagrangian form of velocity gradient? That is the question. Okay, so getting the Lagrangian form of velocity gradient. There are, of course, several ways to do it. Let us do it, for example, component wise. So Lij, that's, sorry, Lij. So that is del Vi over del Yj. Now, if you want to do it in terms of Eulerian, then obviously you have to think of introducing the reference coordinate here, right? So can we think of this as del Pi over, let us say, del xk into del xk over del Yj? What do you think? We can do that, right? Simple chain rule, right? And of course, this xk is the xk bar, the inverse map, okay? The function xk bar. So, yeah, anybody, can you tell me what should I do next? I want to write things in terms of, deformation gradient. So anyway, so del Vi over del xk, what is this quantity? Um, let's see if we can do something here. So can we write it as del over del xk into Vi, the ith component of velocity? Can I write it as del Yi over del t, keeping x fixed? Can we do that? So Vi, the ith component velocity, is del y over del t, keeping x fixed, right? And then you have to multiply this, of course, with del xk bar over del yj. So please, if you're not able to follow, please interrupt me. Just ask me questions. I hope that all of you are following it. Okay. So now what I will do is, you see, you have two derivatives here, one with respect to xk and other with respect to time. And the derivatives, I mean, xk and t, they are independent quantities. When you're thinking of Lagrangian framework, then xk is the referential coordinate and time t is the time. So they are independent quantities. And here you have a mixed derivative in xk and t. And you know that you can change then the order of derivative, right? You must have learned from a math class that if your function f del 2f by del x1 del x2 is same as del 2f by del x2 del x1, and of course you can change the order as long as x1 and x2 are independent. And same thing is here also. This xk and t, they are independent quantities in Lagrangian framework. Okay, so we can therefore flip the order of derivative. Remember, if the derivative, if instead of xk you had yk, then you could not flip the order of derivative because yk and t are dependent. Yk is also a function of time, no, in Lagrangian framework. So then in that case, you could not have changed the order of derivative. Anyway, so let us do that now. So what you have is therefore del over del t of del yi over del xk, okay, and then this is at fixed x, and multiplied with del xk bar over del yj. Okay, so what is this now here? What do you have? Del yi over del xk. What is this? Anyone, can you tell me what is this if you think of in terms of deformation gradient? Yeah, Sri Vandya is right. Fik, right? It is Fik. So this is basically del over del t of Fik. Okay, and remember it's at fixed x. That means we are talking of material time derivative at fixed x. If it's at fixed y, then it's spatial time derivative. But now we're talking of material time derivative. In fluid mechanics, this is what you call big D by big dt. Okay, so and into, this is also interesting. What is this quantity? Anyone? What is this quantity? If you want to think of it in terms of deformation gradient, what is this quantity? Fjk inverse. So Vishwas is saying Fjk inverse. Anybody disagreeing with this? Well, you're quite close, Vishwas. Maybe let us try to explore this. So, can we write this? So, del yi over del xk into del xk over del yk. Sorry, yj. What is this then? Can someone tell me what is this? So, there's a chain rule, of course, and there's a summation over k. What will this be equal to? So, it's a simple chain rule, no? This is equivalent to del I over del yj. But what is del yi over del yj? That's nothing but delta ij, Kronecker delta ij, isn't it? But look at now. Suppose I call this eik, and this I call bkj. Okay, then aik into bkj is equal to delta ij. But you see on the left you have aik into bkj. It is like multiplication of two matrices, right? Matrix A multiplied with matrix B, and that's equal to identity, right? So, and now you know what is this? This matrix A is actually your big F, no? Because it is del yi over del xk. So this matrix A is actually your deformation gradient, the matrix of deformation gradient. So this B must be the inverse, right? The matrix of inverse of big F. Only then it can become identity. So this B is actually big F inverse. So what is then BKJ? BKJ is big F inverse KJ. And go back, your BKJ was del XK over del YJ. Okay, so that's your big F inverse KJ. So I think Nikhil said the correct thing. Vishwas was almost correct. Okay, so this is basically big F. So let me change the color. So this is big F inverse and the kj component of it. Okay, and you can also think of it in a quite simple way, because you are now taking the derivative of xk with respect to yj, so it's the inverse gradient, no? And in its kj, so it's the kj component of inverse function or inverse deformation gradient, f inverse. All right, but now what is this then? So this is, you del t, you bring it inside and you say it is f dot ik. And remember that this dot means it's the material derivative. So f dot ik into fkj inverse. Okay. So that's your del vi over, let's see, what was it? Del vi over del yj. Yes. Which is also lij. So that's the Lagrangian form of Eulerian gradient of velocity, or velocity gradient tensor. So if you try to come back to the tensor form of it, so this is the component notation, no? Component wise, indicial notation. So if I try to come back to tensor form, will you allow me to write that L is equal to F dot into F inverse, right? So this is the thing that we wanted to derive, the Lagrangian form of velocity gradient L. Very interesting derivation, isn't it? Okay, so having derived this, now this is for a general deformation where the body can also deform. Okay, try to, can we try to relate this with the rigid body motion? So in case of rigid body motion, what is big F? So remember, for the rigid body motion, what we wrote was y of x comma t as q of t times x plus b, right? And b of t basically. So what is big F here? Which is basically del y over del x. So isn't that equal to q? So big F is q of t for rigid body motion. So put that back here, what do you get? That means L is equal to q dot q inverse, right? Because F is q. Isn't this what you had for rigid body motion? The velocity gradient was indeed this q dot q inverse, which is W. Okay, so you have derived this general formula and you also verified it with the special case of rigid body motion. All right. Now this L, as I told you, it's a very interesting quantity. And for the rigid body motion, this L is antisymmetric, right? This L is W only for rigid body motion. But for a general motion, L is not antisymmetric. It has both symmetric and antisymmetric part. Okay. So the symmetric part is denoted by D, which is L plus L transpose and half of it. Okay. Whereas the antisymmetric part is denoted by W, and that's half of L minus L transpose. Okay, and if you think of now component wise, then dij is then half of del vi over del yj plus del vj over del yi. Okay, whereas wij is then half of del vi over del yj minus del vj over del yi. Right? I think all of you will agree with this. And I will show you later on that it's the D part which figures in the rate of strain. Okay, this is also called rate of deformation tensor. Rate of deformation tensor. Okay, whereas this W, this is called spin tensor. Okay, and this is related to vorticity that you guys are familiar with in fluid mechanics. But don't worry, don't think of as you being a person from fluid mechanics or you being a person from solid mechanics. As far as this course is concerned, both of you are person of which mechanics? Anyone? Both of you belong to which mechanics? Continuum mechanics. Yes, very good. So don't segregate yourself. You are a continuum mechanics student. Okay, so you have this D and W. D is the rate of deformation tensor and W is the spin tensor. And like I was telling you, it is the D part which will figure whenever you try to derive the rate of strain. So rate of strains, all the strain quantities depend on just the D part. And you see, and that is why this D is missing from rigid body motion. In rigid body motion, L is antisymmetric, and so D is 0, no, for rigid body motion. And that's because when you have rigid body motion, the strains are all 0. Okay, and you just have W part in rigid body motion. Yeah, so now you can ask me questions. Okay, so Raj Vardhan is asking how we change the order. So that's from simple mathematics, no? You mean the change the order of derivative, right? I hope this is what you're meaning. Coming from here to here. So that's simple mathematics. Mixed derivatives are equal. Sorry, I mean going from here to here. It's simple mathematics, no? Mixed derivatives are equal as long as the two quantities are independent. Okay, any other question? So you can ask me also, you can say.
Hello.
Yeah.
Sir, when you wrote V is equal to W plus B minus WB, and then we took a derivation with respect to YK.
Just a second,
So,
let me go there. V equal to W, you mean here?
so before this, when we wrote it as like WY plus B dot minus here, sir,
Yeah, yeah.
then sir, you did the derivative, you took dou Vi divided by dou Yk equal to Wij, dou Ij divided by. So you took the second part as zero. How did we do that? I forgot. I just didn't listen. That's why.
Okay, yeah. See, because the second part, this part over here, does it depend on Y? It is not dependent on Y, no?
Thank you, sir. That's I just didn't hear it. Thank you.
Okay. Any other question?
So how this velocity gradient and angular velocity, whether in any way they will be related in some form, sir? Like although one is vector, another is tensor, but we are writing in the same, like with the same alphabet, and or whether
Yeah.
they will be related
See,
also.
right, right. So you just saw it, right? The velocity gradient for the case of rigid body motion, the velocity gradient is equal to this W here, right? For the case of rigid, where W is
Yes.
the second order tensor, antisymmetric tensor, and this is containing the information of angular velocity. So this angular velocity is this W vector you see here is equal to axial vector of W. So you can extract angular velocity from this big W. If I write it big W as 0, 0, 0, then minus W3, W2, minus W1, 0. Sorry, no, this is not 0. This is
Minus.
W1. This is minus W2, and this is W3. So that's this is your big W, okay, tensor. And from here you extract small w, sorry, again this w, but the vector w as w1, w2, w3, the three non-zero components that is present here. You write it in the column form in this way, and that is called the axial vector of skew symmetric tensor.
Okay.
And this
Sign we
axial
need
vector
not
is
consider.
velocity. Yeah, tell me.
Sign we need not consider. I think only the like W1,
Yeah,
W2, W3.
but you have to see very careful. I have to write in this way only. Here it should
Okay,
be with a minus sign, here it should be with a plus sign, and here it should be with a minus sign. And then you extract and it becomes this. There's a way to
understood.
also write this using permutation symbol. I'm just missing it, but there's a way to write this using permutation symbol also.
Okay, sir, got it. And
Yeah.
also, sir, we are talking right now like representing Eulerian derivatives in Lagrangian space. So whether the opposite also will be doing, like the Lagrangian gradient we can take and then represent in the Eulerian form.
Okay. Yeah, but that is something, it's not useful. What you're saying is, can we think of,
Because Lij is all in the Eulerian frame only. Only thing we are
exactly,
representing in the Lagrangian variables.
right? What you're asking is about this quantity, this gradient with respect to x of velocity.
Correct, sir, correct.
So this is the Lagrangian gradient,
Yeah, I think
and
big G, big G, big grad.
yeah, big grad. So this is that big grad. So I think this is not so useful as far as physics is concerned. You already see that this big grad v is actually f dot. This is f dot, and it is not very useful.
Okay, for our strain computations and all, I think the other derivative only will be coming into picture.
Yeah, for the rate of strains, um, I think there's a way, you can make it useful by doing some mathematics, but at least the way quantum mechanics people have worked out, they don't use this thing so much.
And sir, what is the idea behind writing the rigid body motion in that form, sir? I mean, rigid body motion can be translation as well as rotation, so
The
that's
timer
why
is going to.
the rigid body expression, rigid body motion expression we have written, no, in terms of rotation and the translations. So rigid body consists
Correct.
of rotation as well as translation. So that's why we have taken that form. Or what was the intuition
Yes.
behind taking that form? Because
Yeah,
it
yeah.
was a new for
That's
us.
the intuition. That is the intuition because it contains
Yes.
rotation and translation, and rotation and translation part they are independent of x. So therefore, this
But
q
then
is
X is
independent of x.
figuring, so X is figuring with the rotation component only, because I think we need to get a
Yes.
vector, like we have to extract from that tensor a vector. So we take that X with the Q only. But whether
Yes.
with B, it is independent of that, like B,
Yeah, yeah.
nothing of that sort.
Yeah, yeah, it is. You can see here, no, for example, when you want to do pure translation, put q equal to identity, and you get and you see that it is indeed like that. In case of pure translation, isn't it that y is equal to x plus b? All the quantities displaced by the same quantity b. So
Okay, yes,
therefore,
sir.
you can see x present here with
Understood,
b.
sir.
Yes,
Okay, okay, sir. Thank you.
sure.
Sir, how we wrote B in terms of Z?
Okay, so it's very simple. You just have to equate these two, no? So this is y, and here is another form of y, right? So from here, you keep this q into x as one term and equate it to the first term over here. And whatever is remaining is then b, and I simply wrote that here. Whatever is remaining, I equated it to b. Okay. See, this formula is kind of more physical, because whenever you do rotation, it is about some point, no? It's about some point and along some axis. So the axis information is within q, and by what angle you are doing, that's also within q. But about which point you are rotating, that is not within q. So here, coming to this picture, the point about which it is being rotated is z. So any point x, when it rotates, you can think physically that this vector connecting x with z, it's that vector which is rotating, and its magnitude must not change because it is rotating about z, no? So all the points, let us say if it is this point, then that goes somewhere over here. The magnitude will not change, just the orientation. So therefore, these directions x minus z is going to become q times x minus z. And then you see this final y, you can get it as this z plus q times x minus z, and that is what I wrote here. Okay. Yeah, ask me.
Sir, if Q is equal to I, then B will be 0, sir. Means the translation would be 0 because the equation you have given B is equal to Z minus QZ.
Hmm.
Then if Q is I mean identity tensor, then B would be 0, sir.
Okay, yeah, I think that's a very good point that you mentioned here. So I think I need an extra thing here. So I wrote here, no, this y equal to this thing. It is kind of pure rotation. So I need to add to it something more, some b prime. So that's a very nice point. So what I wrote here, it's corresponding to pure rotation. There is no translation which was added here. So that could be added as b prime. And then you have here b equal to this plus b prime. B prime doesn't mean it's the derivative of b, it is some other vector. So very good point.